Morning. Is that the math wall from school?
Yeah. Like that? All right, I'll be back.
Yes. Yes. All right. I know. Class is starting and you're not prepared. Come here. There. Goober drooled on herself.
All right. Do I have audio? I'm plugged in. Okay, that's good. The mic seems to be working. All right. We have a little visitor again today. So cute.
Every time I go and I start the laptop up now, she thinks we're Skyping with grandparents. She wants to be in front of it, so she gets fussy, and I'm like, it's class time. So now she just likes to sit and watch everybody else, and she's just like, okay, let's do this. And I'm like, you have no idea what's going on.
No idea. That's all right.
But we were teething and goobering all over everything, so I'm trying to keep.
Of course, right.
Yeah.
Do I have any fun kid backgrounds? I don't think so. No. Just Legos. That's all I got. She's a little too young for that.
Oh yeah. We're working on terrorizing the dog and trying to crawl, so.
Right.
Legos in a couple of years.
Mine are old enough now where the cats finally let them pet them. They're no longer scared of the boys. The boys have learned to move slowly, approach gently. And, for years, the cats wouldn't even let them get close.
Oh, yeah.
No way, dude.
I've never seen a dog jump like a cat until I had her. She reaches out, and the minute she touches him, it's nope,
Like,
we're going.
whoa.
Out the
Yep.
door.
Yep.
Oh,
All right. I guess it's time to get going. How are you doing today, Brittany? Good? All right. Oh, you're still muted, but it's okay. You got the thumbs up. It's all good.
Yeah, I'm good. I'm just going back and forth between trying to get my headset set up so that my husband can do his classes and I can do mine without
Right.
interfering with either.
Yeah. Yeah. I feel lucky that we've got like an extra office. I can shut the door and yeah. But the problem is, I think I've mentioned it, like, is a glass door. So then the kids come in and they're like can I? Dude, it's so funny. It's all
I
good.
got hubby in the office, my kids in the dining room, and I'm in the living room, and we're trying to stay far enough away where we're not interrupting each other's lessons.
Right.
And my husband's on conference calls, so it's just, and then the dog just rotates from room to room.
So who it's gonna annoy it? Like, it's like, oh my gosh. Boy, I was looking ahead at what we have left. Like we are almost done, man. We are really in the stretch run here. Here's our calendar reminder here. Look at this. We could take off a couple more here. We're focusing on homework questions from 5.1 and 5.2 because that's what the quiz is on. But if we have time after that, we'll do some more examples, and then we have some 5.3 examples, which like we're getting to like really good stuff now. For the weekend, I want you to watch 5.4. I have a news post coming up with the quiz that has links to those. So next week we'll go over questions on 5.3 and 5.4. And then we're going to watch 5.5 for Thursday. And we'll have one last quiz. And then Monday we'll go over 5.5 questions. We talked about adding that Monday class. Tuesday we'll do some review, and then our final exam will be posted. So like, man, we are almost there. I know that there's a lot to do, and we might not get to everything in class. And so I think last time we had a nice discussion after class. People had questions. We'll do that same thing today. And then if you have other things that you want to ask about, you can always just email me, and if we can't answer via email, we could coordinate a time to chat, spend 15 minutes like office hours. Sometimes that's really effective, that one-on-one, just chatting, getting some specific questions. So feel free to email me. We've all got things to work on, but we can definitely find some time to talk together if that would be helpful. So yeah, so that's my plan for today, is start with homework questions. Let me get the homework up here. By the way, I'm going to give you one last survey kind of near the end of the semester. I think you got official course evaluations, but they're kind of worthless this semester. Usually I'd say like, give me your feedback there and I'll use it for but like, it's kind of irrelevant this semester. But I do want to ask you about the things that we've done and like what worked and what didn't in case we go online again for the fall. I kind of want to know, like, okay, of the things we did, what was good? Of the things we did, what should we not do again in the fall? And are there other things you would like to see? So basically, I'm just going to have like 3 open-ended questions, not like a survey, strongly agree. Just like, okay, of what we did, 2 days a week, watching videos, posting quizzes on, like all the stuff that we did, what was good? Should we not do again? And then is there other stuff that you would like to have available? So like, that's kind of just, I'm going to be actually part of a planning committee for fall. The fact that we're forming a planning committee to me is like a sign that they're really thinking seriously about it. So I want to know, like, do you have any good ideas? So look for that email or with a survey. All right, so I have 5.2. We have 5.1 and 5.2. Got them up here. I can open whichever one you want. So who would like to get us started? I got to open the chat window here. All right, I got that open. Who would like to start us with a question from the homework?
Can you go over 9 from 5.2?
5.2. Okay.
Confused on the presentations.
The notation you said?
The representations.
Oh, the representations. Okay. All right. Let's see. Come on. Loading, loading, loading. Gotcha. All right. All right, I can see how that would be confusing. All right. Let's take a look here. So let me write down what the Riemann sum is in general. There's a lot of funky notation in it. So the Riemann sum is the sum I goes from 1 to n of f of u sub I delta x sub I, where u sub I is an x value in the, this is kind of weird, but in the ith interval. So u sub I is an x value. So here they've given us this partition. So let me write this in a number line. We're going, you can see here, we're trying to go from 0 to 2. In fact, you know what? Let's draw the graph too. Let's draw the graph too. So we're trying to go from 0 to 2. We have the function, it's y equal x. So that also goes from 0 to 2. Okay, so here's the graph, y equals x.
I see where I messed up. I didn't even notice that there was a graph right there, the f of x.
Sure, but I think I still want to do it. So even if you're okay, I think this is worth doing. So I'm glad you figured out what you needed here.
I was wondering what the function was.
Right, you're like, well, how do I evaluate? Yeah. This is why like the notation here is killer, because like it doesn't like lay it out for you. So let me partition it the way they said. So 1 to 2 is there at the end, and looks like the rest of them are split into quarters. Quarter, a half, 3/4. Okay, so those are our partitions. And then what these u's are, the u's are what x value should you use in that interval to make the height of the rectangle. So 1/8 will be right here. So there's 1/8 right in the middle. 3/8 would be right in the middle here. What is this? 5/8 would be right in the middle for that one. 7/8 right in the middle for this one. And then 9/8 is not actually right in the middle, it's just another 8. So I don't know if I can label these, maybe down below. 1/8, 3/8, 5/8, 7/8, 9/8. Kind of like hunched over here. I like the ability to write, but like I feel like you just see me like hunched over all the time. So what the notation means here is we're going to add up the function value at 1/8 times, we'll call it delta x sub 1, the width of the first interval, plus the function value at 3/8 times the width of the second interval, plus the function value at 5/8 times the width of the third interval. 2 more here, function value at 7/8 times the width of the fourth interval, plus the function value at 9/8 times the width of the fifth interval. And you can see on the picture what that is that's the area of all those rectangles, 5 rectangles. And so it's the area of all those rectangles. That's what it is. Now in this case, to Christopher's point, the function is kind of hidden in here. The function is f of x equals x. It doesn't get much simpler than that once you recognize it there. So the function value is going to be 1/8. The width of that first interval is 1/4. The function value will be 3/8, and the width will be 1/4 for that one. Function value is 5/8, width is still 1/4. Function value is 7/8, width is 1/4. Function value is 9/8, and then the width for that last one is 1. It's wider. That fifth interval is wider than all the others. And then you just add all those together, whatever that is. It's going to be a bunch of 30 seconds. 3 30 seconds. 5 30 seconds. 30 seconds. 30 seconds. Let's see, 9/8. I guess we should make that into 30 seconds as well. 30 seconds. That's 4:36. 30 seconds. It's too early to be doing this much math. 4, 9, 16, 52. I feel like it's got to be, it's definitely even. 26 16ths. That's still even. 13/8. All right, that's what I got, 13/8. This is one of these where I know somebody did this on the test. I saw this a couple people say, okay, I know my process is good. Something doesn't look right with the answer. So my process is definitely good here. I don't know if the 13/8 is exactly right, but okay. So Christopher got his question answered right away. Does anyone else have any additional clarification questions needed on example 9? This is number 9 from 5.2. 5.2. Okay, excellent. And we're working on homework questions for those who just joined us. Morning, Lorenzo. Does anyone have any additional homework questions? 33, Sandra said. Same section? All right. So we are supposed to, we're not going to actually find the Riemann sum here. That would be impossible for you. Actually, for me too. Well, no, I mean, anyway, it's complicated. So we're gonna try to express this as the limit of a Riemann sum. So a reminder, the way the Riemann sums work is they're a sum. You have a function value at a u sub I times delta x sub I, and then you add, so those are the rectangles, the area of the rectangles. And then you add them up, you get I, you add up, you get n rectangles. So, so we're going to say equals, I'm going to put a space here because there's going to be a limit in there. So I'm going to add up, I goes from 1 to n, and the function is sine here. So it would be sine of u sub I, delta x sub I. And then what to get the definite integral, that has to be the exact area. So even if you have 1,000 intervals and you break it up in these tiny little intervals, it's still not the exact area. The definite integral has to be the exact area. So all that means is we take the limit, I'm not going to have space here, but hold on, I can cheat. You take the limit as the maximum width goes to 0. So whatever that widest interval is, you make that widest interval go to 0, then you'll have infinitely many, infinitely small intervals, and you will get the exact perfect area, which is what you're trying to get.
Okay.
So you can see what I focused on there is I took the function and just evaluated it at a u sub I.
Mm-hmm.
And then I've had this delta x sub I is always there. The sum is always there. And then this limit in the front is always there if you want to get the definite integral. So the only thing that really changes is the function.
Oh, okay. I I asked like the same question last time, but I just wanted to check if I understand why. So for this one, we don't have to do the left endpoint to find the.
Right.
We don't have to
Right.
do it.
Mm-mm.
Okay. So
No.
the key is just the expression. They didn't ask us to find the exact answer for that one.
Right. Right. That would be very, very difficult. That would be very difficult. So here it's just asking us to write it as the limit of a Riemann sum. And so this is the Riemann sum. So the only thing you have to change is the f.
Okay.
Mm-hmm.
And concerning the homework, some of the question we were not supposed to do anymore 51 from 5.2. It is because we cannot do at this level find
Well,
the exact value.
it's not that we can't do it. We
Uh-huh.
could. And Dr. Sugar made videos about how to do it.
Yeah.
But we're just choosing to save ourselves the pain
Okay.
because we have enough pain in our lives right now.
Okay. So we will not have it for the quiz,
No,
for the exam.
no. But you could do it. Like you totally, everyone in this class has the capability to learn how to do it. But it's just kind of this like, you have these important topics and then it's like outside of that. It's like
Okay.
interesting, valuable, but we had to make some choices about what we're going to do. And so we're not going to cover it. It's not going to be required. And if you never learn how to do it, you can totally do fine in all the rest of your calculus classes.
Okay.
So,
That was all.
okay. All right. Any additional, we're still working on homework questions. Any additional homework questions?
51 from 5.2.
All right. So these are the ones that are optional. So we're not going to do letter A. Like we're not going to do that using a Riemann sum. Those are the ones that we talked about.
I just had a question on solving them. You don't have to, but it says Riemann sum, and we know the Riemann sum is equivalent to the limit as n approaches infinity. So could we just go straight to that?
Yeah.
Oh, all right.
Yeah. So if you want, see how this one's different from Sandra's. This one says actually find the definite integral using a Riemann sum. So if you actually had to find it, here's what's different. The difference is you're not going to be able to just write it with that u in there because you can't say, well, it's going to be the limit as the maximum delta x sub I goes to 0 of the sum I goes from 1 to n u sub I minus 4 delta x sub I, because you can't actually find that. So if you actually need to find it, what you do is just choose delta x sub I to be constant, make them all equally spaced, 1 minus 0 over n. So the whole width of the interval, divide by n. So just choose the delta x sub I to be 1 over n. And then this is where Christopher's talking about the endpoints. And Sandra was asking about the endpoints. You know, do we use these endpoints, other endpoints? I would use u sub I to be right endpoints. And in this case, what that would be is it actually would just be I over n. You can kind of list them out and see, well, 0, then it would be 1 over n, and then 2 over n, and then 3 over n. I just keep adding them up, 4 over n, plus all the way down to 1, n over n. And so you can use right endpoints. And so then, this is what Christopher was saying, to make the width of the widest one go to 0, well, I could just make n go to infinity. And then I would have the sum, I goes from 1 to n. My u sub I is I over n minus 4. My delta x sub I is 1 over n. And that is a limit that you could learn how to do, and you could definitely do it. And you can get the actual area. You can find the definite integral of doing that. So, but again, we're not going to ask you to do that. I'm just kind of doing that here for reference.
If we were given this problem, would you expect us to write out the relationship between the max delta x I equals 0 to n equals infinity? Or could we just go straight to n equals infinity?
Well, I'm not going to give you this question, but because this is the topic, we're just not going to be asked this. But in the future, if you're asked to do a Riemann sum, you can jump right to that. I mean, it's good to have the connection, it's valuable, but it would be totally appropriate to jump right to the limiting statement like that.
Thank you.
Yeah, but what I'm gonna ask on the quiz and the test is just like lower and upper with 4 subintervals or 6 subintervals or something like that. Or maybe, to Sandra's point, maybe I would ask you to write it as the limit of a Riemann sum. Right? I'm not asking you to find the Riemann sum, just write it as a Riemann sum, but not actually to find it. Okay. All right, good questions, good questions. Any other homework questions? Good morning, Talante.
Good morning. I'm sorry. I've been at work and stuff. That's why I haven't attended class.
I know a lot of people's schedules are totally thrown off, and work schedules have changed. And, yeah.
All right. Yeah, I'm good.
Okay. All right. All right. Chantel had a question about 67. So there's some kind of more advanced ones here, not like advanced like lots of work, but advanced like ideas. Like, what is this question even asking me? So this is important. This is an important one for us that we will see in 5.3 and beyond. Like, what does this integral even represent? And what would its units be? So here is the key. If we think about a definite integral from 0 to 5, this is a force function. So it's in newtons. It's interesting, I always capitalize newtons because it's named after the dude, but apparently the unit is not capitalized. F of x dx. I'm going to write this as a Riemann sum, not because that's valuable, but because it will help us analyze the units. So this is going to be the limit. I would not do this every time for you, but I'm just like, you should not do this as a student, but I want to explain what I'm thinking. So when I see the f of x dx, in my mind, I'm thinking that started as adding up a bunch of mini little forces, right? These are forces in newtons, multiplied by some delta x sub i's, which would be distances in meters. And so each little multiplication would be a newtons times meters. And then I would add up the next one, newtons times meters. And I'd add up the next one, newtons times meters. And I would keep adding up all these newtons times meters. So each one would be newtons times meters. So what I would get is something newtons times meters, whatever that is. I know what that means. You don't. You haven't done that kind of thing yet, probably. But whatever it is, it's newtons times meters. Because, and you can look back at the original integral, you can see the f of x is newtons, and then if x is measured in meters, dx is like a little delta x. Of course, it's infinitely small in the dx, that's in the limiting process, but it's in meters. So you just multiply the units of the function f of x is in newtons times dx, which is in meters. So the newtons would be whatever, or the units would be whatever newtons times meters is. That happens to actually represent work. How much work does it take to move an object? So that's the answer to the question, Newton meters. But you can do this anytime. Anytime you have an integral like this, you can just take the units of the function and multiply it by the units of x.
That's what I just read the problem, and it literally just said like you're multiplying the force in newtons by measured in meters. So I'm like, I knew that was the answer, but I'm like, I didn't know what work if this was on the test and I just wrote down newtons times meters, is there really a way to show work on this?
Nope. I mean, you could show like what I did. That's like,
yeah, that's what I was like. I'm like, how do I?
Super excessive. Like it's super excessive. Yeah. Like it's more interesting to me is what if we integrate say from 0 to 5, velocity function dt, where velocity is in meters per second, and then t, of course, would be seconds. So the question is, what are you evaluating? And in fact, this is in section 5.3. They're kind of hinting at that coming up. But you're taking meters per second, and you're multiplying it by seconds. So what are you getting?
Meters per second squared?
Nope, good thought. Good thought, but it's meters per second. If you write out the fraction, it makes it a little bit easier to see. It's meters per second times seconds. Does that help?
Yeah.
So what would the units be if you take meters per second times seconds?
Meters.
Right, Lauren, so you just get meters. You just get meters, the seconds are eliminated, and so you just get meters. So in fact, what you get, if you integrate the velocity, now velocity, I don't know, we've talked about this briefly. Velocity can be positive or negative. You can move forward or backward. And so if you integrate velocity, what you get is how far you are from where you started. It's called displacement. You get your net change in displacement. It can be positive, could be negative, because you could end up behind where you started. But you get meters. And so to Chantel's point, like how would I show, I mean, the work that I guess what you could show is like this. Like that's, if you wanted to show some work, you could show that. The benefit to you to showing work is if you recognize that you multiplied them, but say you did it too quickly, and you said, I don't remember who it was, but said meters per second squared, but you wrote down your work, I could see like, oh, you were looking at the units and you knew that you should multiply the units. You just kind of did it too quickly and multiplied them wrong. You could get some partial credit. You know, if you just write down an answer and it's wrong, it's really hard to give partial credit if I don't know what your thinking was. So, but I don't think I would have to see any work for this problem at all. What are the units? Well, you just multiply the f of x times the x, and so you get newtons times meters. And I think there's another one too, if I remember correctly. There's another one, wasn't 69? Oh, 69 is what we were just talking about. So wasn't 69 also assigned? Yeah, 69 was also assigned, and that's the velocity I was just talking about actually. So v of t represents velocity in meters per second. T is measured in seconds. What are the units of the integral? It would just be meters. Yep. In fact, that's related also to 63 and 65 as well. Similar things about units. All right, good discussions. Are we good with that one, Chantal? Okay, good. Any additional questions? Still chipping our way on homework here, if anybody has any additional homework questions. Anybody recognize my new cool background, by the way? Do you know where you've seen it before, but maybe not like actually seen it? You know what
the walls in building D?
Yeah, good catch. Yeah, Mike. Actually, like that's a locally produced thing. Like Professor Wheaton worked on that. Professor Bailey, Dr. Bailey, and Professor Bainan. I don't know if any of you have had any of them. They actually worked on this, and then we had one of our graphics design persons kind of pulled it all together. It actually goes, of course, like way far beyond this. It just kind of crops it to show in Zoom. But is there anything? Oh, there is some stuff. Look, do you see right here? Calc 1 stuff. Is there anything else? I can't see what else. Can't make it any bigger. Hold on, can I make it myself bigger? Oh, shoot. No, I can't make it any bigger. I'm trying to like zoom in. I think the rest of the stuff is not Calc 1. So anyway, it's kind of cool. All right. All right, last call. Homework questions. Oh, Lorenzo's on. 5.2, number 39. Oops, I was right in there. Why did I leave? Is that one of the ones? Okay, 39. Oh, did we? This sounds familiar. Hold on. Let me see.
We
here.
did that one. Teacher.
Yeah, I was just going to bring it back up here, and we can talk about it again. Okay, here it is. So let's talk about it just again here. So we're going to approximate the area. Is this the right one? Is this 39? No, wrong 39. Maybe we didn't do it then. I feel like we did, but wait, what? Oh, this is Thursday. I like had the wrong date here. Thursday, 4/28. Thursday, 4:30. Okay, so maybe we did. Yeah, maybe we didn't do it. I felt like we did it, but now I'm not seeing it here. So that's okay. I guess we will do it again. We did do 39, but this is not the right 39. This is 39 from 5.1. Okay, so let's grab it then. Is there a particular part of this, Lorenzo, that you were wondering about? A, B, or C?
It was kind of
just the whole thing, or
yeah.
Okay, yeah, no worries. That's fine. I was wondering if it was the technology. We can show how to do it on the calculator. It's a useful skill, especially if you're doing the lower and upper. I had one student email me a question about did the lower, did the upper, and then tried to use try to find the actual one, and it wasn't between like it should have been. And so this is a good, like, if you know how to use your calculator to get the actual integral, you can kind of, if you did the lower and upper, you could kind of go like, well, my lower should be below the actual one and my upper should be above it. So let's focus on A and C, because B is just a more complicated version of A. It's the same idea. Okay, so I like to do a graph. So x squared minus 4 from 0 to 8. All right, so x squared minus 4, 0 to 8. That's going to be really big. I don't want to do, so negative 4, but then it's going to like grow really quickly. Oops. This is not going to be really accurate. My scale is going to be off because 8, you see what I mean? Like at 8, it's going to be, what is the y value going to be? 60? Right, because it'd be 8 squared, 64 minus 4 is 60. So my scale is not quite right. It doesn't look, it's not right at all, in fact. I guess maybe I could, I don't know. I don't want to stress about it too much, but I suppose I could just start closer here and then go way up there. So it starts at negative 4 because it's shifted down 4, and we're going from 0 to 8. I guess, oh, sorry. It crosses at 2 because 2 squared is 4. 4 minus 4 is 0. Okay, so we're supposed to do 4 subintervals. So that's 2, 4, 6, 8. And for B, you would just actually do every integer. You do 8 subintervals, so you do 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and for A, we're supposed to use left endpoints. Left endpoints. So I'm going to make these red. So for each interval, I'm going to go to the left side and then down to make my rectangle. Oh, this one's kind of boring. The left side would be 0 there. Left and left. So what I'm doing is for each interval, like from 4 to 6, I'm using 4 and going up to the function there. I'm always using the left endpoint. Okay, so then what I want to do is I want to add up the function value times the width. There's going to be 4 of them here. And the function value is going to be from the left endpoint. Maybe let's write those here. I guess we can do that, right? F of 0 will be -4. F of 2 is 0. F of 4, 4 squared minus 4 is 12. 16 minus 4. And then F of 6, 6 squared minus 4 be 32. So over in my sum, I'm going to do f at 0 times the width 2 plus f at 2 times the width 2 plus f at 4 times the width plus f at 6 times the width. And then we have all those function values, -4 times 2, 0 times 2, 12 times 2, and 32 times 2. -8 plus 0 plus 24 plus 64, 680. 68 minus 8? No, 88 minus 8? Yeah, 80. So how is that, Lorenzo?
Good.
You okay there?
Yeah.
Okay. Do you think you can do it on your own with 8?
Yeah.
Okay, good. Let's talk about the technology then. You can use this actually super easy in Desmos. Desmos is great. You can actually type int. Check this out, int. Oh, it gives you an integral. And then you just type in 0 to 8 x squared minus 4 dx. Boom. That looks like a fraction to me. You can even click this fraction button. Boom, it gives you a fraction. Yeah, it's pretty cool. So 138.7. You could do it on your calculator as well. And if you don't have that, if you want a calculator and you don't have one, email me. I can show you how to download one. I posted links. It's been a while since I've posted them, but you can download the same thing that I'm using right now, this emulator. You can download it to your computer if you need that. So just let me know. Sorry, it's on my other screen here. And so that's under math, and then there's this function integral, enter. And so you just go 0 to 8, and then x, whoops, I had an extra parenthesis in there. Sorry, I guess there was already a parenthesis. X squared minus 4 dx, and hit enter. There's the same answer, of course. And if you want a fraction, you can go math to fraction. There's the exact answer, 416 thirds. So it looks like using left endpoints was an underestimate. And you could see that here. I don't know if you could see that coming, but you can see how we got a little extra negative in the first box. There's more negative that we got because of this extra. I don't know if you can see it here, if I can shade in. This here, we got a little extra negative, but then we lost all this positive, we lost all this positive, and we lost all this positive. So we were severely below what the real value is. So that's why we're like 50-some below. We're like 50% less than what it should be, because we missed a lot of area by doing the left endpoints. All right. I think in B, using right endpoints should give you a big overestimate. I would guess probably something like 170. I'm just ballpark figuring that it's going to be above what the actual one is.
Can we please do B? I did it, but I got 67. So.
Oh, which is like, yeah, like that doesn't, yeah, it should be more. Let's take a look then. So what I'm going to do is I am going to not draw the whole function. I lose my mouse sometimes. Like, where did it go? I'm just going to draw the number line because that's really all that's relevant here. All right, 1, 2, 3, 4, 5, 6, 7. So we're going to use for each interval, we're going to add up all the rectangles again. But we're going to use equally spaced. So delta x is actually going to be always the same. It's going to be 1. And then our u sub i's are going to be right endpoints. So 1, 2, 3, 4, 5, 6, 7, 8. So we'll have f at 1 times 1 plus f at 2 times 1 plus f at 3 times 1, etc., down to f at 8 times 1. So I'm taking the right endpoint of each interval. I'll evaluate the function there and then multiply them by the width 1. Okay, so far?
Yes, I saw my error.
Okay. Should we keep going?
Yes, yes.
Just keep going anyway? Okay.
Mm-hmm.
So this will be 1 squared minus 4 times 1, 2 squared minus 4 times 1, 3 squared minus 4 times 1, 4 squared minus 4 times 1, 5 squared minus 4 times 1, 6 squared minus 4 times 1, 7 squared minus 4 times 1, 8 squared minus 4 times 1. Plugging all of those right endpoints into the function. So -3, 0, 9 minus 4 is 5, 16 minus 4 is 12, 25 minus 4 is 21, 36 minus 4 is 32, 49 minus 4 is 45, and 64 minus 4 is 60. So let's see, 2, 14, 35, 35, 65. Oh, we're much higher than I thought. No, oh, what did I say? That's 110. What did I say? That's it, mic drop, I'm out.
What's going on?
That's pretty good, come on. But here's how I knew that, by the way. I knew it was gonna be above. So obviously it's gonna be more than 138. It's definitely gonna be more than 138. And you know how far below, like the lower estimate was really low? It was really low because we had all these huge ones. Well, for the eighths, the errors weren't going to be as big because you have more subintervals. So the above errors weren't going to be as big. So I was like, well, it's not going to be as much above as this one was below. Still, that's seriously impressive, though.
I think you just earned back some donut points for that one.
Oh, that's too good. That's too good. You know, once in a while, I get something right. Oh, brother, we're getting loopy. We're stuck in our houses on quarantine. We're getting loopy about
April's like
rectangle
the longest
area.
Monday that won't just go away.
Right, it just won't. Just won't. Supposed to have nice weather this weekend though, so we'll be able to get out. We're starting to get into like, you know what, I'm gonna invite some friends over. We're gonna sit on the patio at opposite sides and like hang out one friend at a time. I need some interaction. at least you all, like there's, we talk, not everybody has their camera on, but we talk. There are a bunch of people talk. My stats class is the worst. Like they're great. They're fine. They're good students, but none of them talk and they all have their cameras off. So I'm only interacting with the chat. Like here we have a bunch of people chat and, it's, anyway, I don't mean to be too hard on them. Let's talk a little bit about 5.3. If you have more homework questions, I'll hang out after class and you can do more homework questions on 5.1 and 5.2. I'm happy to answer those. And then the quiz will be posted right after class. And in that post, I also have links to 5.4, which you should watch for Monday. So, but let's talk about 5.3. 5.3 is really cool. I want to talk about specifically, I did post this practice, by the way. You can download it if you're interested. It's right here, linked on the most recent news post, or it is also under Unit 5. There should be 5.3 examples are there also. I just want to talk about part of it. We could talk about more of this on Monday. The Fundamental Theorem of Calculus Part 1 is the less interesting part. This is it's very theoretical. And I'm sure you will have homework questions about it. It looks really weird, but it's not the most valuable one. And it's more of like, you learn it here to kind of prove Part 2, which is really valuable. And then in Calc 2 and Calc 3, it probably comes up twice. So it's a very it's like this important theoretical result that you use twice. So we're not going to talk about it today because I want to talk about Part 2, which is way more valuable, super interesting, pretty much the foundation for all of Calc 2 and Calc 3. So that one is more interesting. And this connects to the antiderivative. And this is really interesting. If you haven't watched these videos, it's kind of a surprising result. Like, why does this work? So suppose you have a function f. It's a continuous function, and you're integrating it from a to b. So you're doing this definite integral, right? A definite integral, which we have learned so far is area or this Riemann Sum thing. Okay, here's what this theorem says. If capital F is some antiderivative, remember the antiderivatives at the end of the last chapter? Well, if you want this definite integral, the Fundamental Theorem of Calculus says you can take that antiderivative and evaluate it at your upper limit of your integral and subtract evaluating it at your lower limit. So a definite integral, you actually don't need to do any rectangles. You don't need to do any sums or limits. All you need is an antiderivative. So here's how this works. Evaluate the definite integral. So the first one here, f of x is x squared. So we're going to use capital F of x for the antiderivative. So you had a question like this on your test. What's the general antiderivative for x squared? Anybody answer that?
X cubed over 3 plus c.
Very nice, Christopher. X cubed over 3 plus some constant. So it's interesting here. If you'll notice the Fundamental Theorem, if I can zoom in here, I don't know how you are with your grammar, but there's an article in here that's important. You know, the articles like the or an. So you have a definitive article means the, and then or a definite article means the, and then an indefinite article means like a or an, like some general one. If you'll notice, it says f is an antiderivative. It doesn't say which antiderivative. So you can pick whatever antiderivative you want. So the point is the c. Any number here is fine. If you wanted to make your life as easy as possible, what's the easiest c?
0.
0. So basically ignore the c in this context. So what we're going to do is we're going to say, well, this is going to be our antiderivative evaluated at 2 minus our antiderivative evaluated at 0. And the notation, there's a lot of notation in calculus, you know that. The notation we usually use here is we write the antiderivative. That's our x cubed over 3. And then we put a vertical line and we say 0 and 2. And what that means is evaluate it at the top one and subtract evaluating it at the bottom one. It's just notation, so we have to write less. So it's just 2 cubed over 3 minus 0 cubed over 3, and you get 8/3. No rectangles, no limits, no ends, no i's, no nothing. It's just the antiderivative. Any antiderivative, pick the easiest one possible. Evaluate it at the upper limit and subtract evaluating it at the lower limit. Do you see that right? That's this guy right here. Whoop, whoop, here. Fundamental Theorem of Calculus, right there. That's it. So you're integrating from A to B. I'm trying to do this as I'm looking at it. It's like reversed. It's weird. You have f prime right here. There's f prime. And so you have f, which would be the antiderivative at B, and then you can't see there, it's off screen, but minus f at A. I should see if I can shift.
The difference between an antiderivative and the antiderivative again?
Well, so the general antiderivative is this one with the plus c. And so when it says an antiderivative, it just means any antiderivative. Then you can have c be whatever you want. That's all it means. The an antiderivative, just pick any antiderivative. So you got to pick something for c. Well, in fact, you don't need to pick something for c. You could leave c in there if you want. So what if we did x cubed over 3 plus c, evaluated from 0 to 2? So what if we did the general antiderivative?
C's cancel out.
They always will cancel out. So they're kind of pointless to include. That's why the c doesn't matter. So you can just pick any antiderivative. That's what the an is. It's an indefinite one. Pick any antiderivative you want. And so we always just pick c as 0. We just kind of ignore the c when we're doing these definite integrals.
Would this work if you did a second antiderivative?
What do you mean by a second antiderivative?
You get an antiderivative, and then you get the antiderivative of that. Would that answer be the same as the first?
No. Nope. You only go up one antiderivative. That has a different meaning. So when you have this definite integral, you do just the antiderivative of x squared.
All right, thank you.
All right, let's try another one here. So antiderivative of x cubed, again, another power rule, x to the 4th over 4. It's weird, we're doing the reverse of the derivative power rule. One of these things that happens on the final is people go the wrong way. You're so used to taking the derivative. We've spent 3 months taking the derivative, and now we have to go backwards. So that's easy. It's easy to mix those up. And then x squared over 2, and we're going to evaluate this from 1 to 3. And so that would be 3 to the 4th over 4 plus 3 squared over 2 minus 1 to the 4th over 4 minus 1 squared over 2. Let's see here, 81 fourths plus 9 halves minus 1/4 minus 1/2. I'm feeling a little lazy right now. Ooh, no, this is fine. 81 fourths minus 1/4, right? Let's put the fourths together. 81 fourths, sorry, 81 fourths minus 1/4, and then plus 9 halves, but then it actually becomes plus 1/2. That's good. So that's 80 fourths plus 10 halves, which is 20 plus 5. So it's 25. That actually worked out pretty nice.
I probably have a Doug question. Why is it 1 to the 4th over 4 minus 1/2, like 1 squared over 2? Would that be plus, or is it?
Oh, shoot. I don't know. I don't know what I was thinking.
Okay. No, I was just wondering. I'm like, it's still plus, and then like the unit minus the. Okay.
Yep. Good catch. So this should be a plus also, but that makes this a minus after we distribute that negative. And so then it makes this 8/2. So it's only 24. Yeah, I just lost my sign there somehow. Somehow my plus, clearly a plus, became a minus when I went over here, but it should definitely, they should follow the same function. It should be the same function evaluated at the 2 endpoints. Yep. Oh, I just blew the donut point I earned with all, oh man, I just gave it right back. Just gave it right back.
I also have a question. So when it says, when you got the 81 over 4, how did it turn to a minus 1/4?
Well, what I was doing is kind of combining like terms. So I was thinking of this 81/4 plus 9/2. If you distribute the negative, negative 1/4 and minus 1/2. And then I was combining the fourths and the halves.
Oh, okay.
Yeah. You could do it however you want. You could type that all in your calculator. It's just arithmetic from there. The calculus part is finding the antiderivative. And then once you plug it in, it's just arithmetic after that. You can use your calculator if you want. I'm not stressed about that. I mean, we all should be able to add fractions, but we're also like kind of stressed. You want to make sure you have it right. So feel free to double check with your calculator there. Let's do some trig ones here. Sine of x from 0 to pi. Do you remember the antiderivative? Don't say it out loud. Don't say it out loud. 10 seconds. The antiderivative of sine of x. Okay, I have a question for you. Click on participants. And then check yes or no whether you're confident that you know the antiderivative. Yes or no, whether you're confident that you have the antiderivative. Okay. Pretty confident. We got about half. If it's okay, I would like to hear from someone we haven't heard from today. So I'm gonna go. Oh, Javante, are you unmuted? Do you want to answer?
Yeah, the antiderivative of sine x.
Yes.
Negative cosine x.
Nailed it. Nice. Yeah, very good. Very good.
Yeah.
That's because the derivative of cosine is negative sine, so you kind of need that negative there to counteract that. So that's exactly right. We're going to evaluate that from 0 to pi. So we get negative, I'm going to just put that out in front, cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. That is way too many negatives. That's negative, negative 2, so we get 2. So check this out. Here's what we were doing. The definite integral can represent area if the function is positive. And so the definite integral can represent area. So from 0 to pi, sine of x looks like this, right? And then it continues on after that, kind of, etc. So the area underneath sine of x is 2. The area underneath one of those arcs is 2. It's unexpected. Like, it's a trig function. Why should the area be a whole number? It seems weird. That's what it is. All right, let's try cosine. This one, the antiderivative is sine, because the derivative of a sine is cosine. That one's antiderivative is sine. From 0 to pi, that's sine of pi minus sine of 0. This one is weird. You get 0 minus 0, which is 0. Huh? How do you get a 0 area? Maybe it's not area. Let me draw that one. Cosine starts at 1 and continues on after that. Here's pi. Why would we get 0? Does anyone know?
There's no arc to measure.
That's right here. I mean, I've got the arc, and I've got like here and here.
Negative. It cancels out.
Yes. So Chantel is right that it's not necessarily area. It's area if the function is always positive. But if you recall, the Riemann sum, the whole definition of this definite integral was this Riemann sum, the sum f at u sub I times delta x sub I. Well, that function value, that can be negative. So interpreting the definite integral as an area is not going to work if the function has negative values. So what Chantal is saying is that if you look at these two regions here, the one above and then the one below, they're the same area. It's the same shape. But the one above is positive integral. The one below is a negative integral. So the two of them cancel out. That's why you get 0. That was a good insight on that one, Chantal. So we just have to be careful. It is possible to get negative integrals. We don't always want to interpret it as a positive area. It definitely is possible to get a negative. All right, good questions, good discussion. Any other questions on these? Okay, I think that's a good place to stop. We'll talk more about the rest of this on Monday after you watch those videos if you haven't already. So on Monday, or not Monday, I keep saying I'm onto it. I caught myself. Tuesday. You're gonna have watched 5.3 if you haven't already, and then also 5.4. And then the last section is 5.5. So we are there. It is like visible. The end is in sight. The light at the end of the tunnel is hopefully not a train. It's a light. It's close. The end is near. So 5.3, they're linked here on the home page. And actually, if I hit refresh, there should be a new post. Dun, 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 dun. Yep. Okay. So quiz is attached. Dropbox is here. There's a bunch of videos. Hopefully, you've already watched the 5.3. If not, don't wait too long. We've got a bunch of videos from 5.3 to watch, and then 3 videos from 5.4. And so we'll talk about all of that on Tuesday, and then we'll work on 5.5 for Thursday and the following Monday, and then Tuesday will be our final. We are so close to the end. We're in the stretch run. Yep, so I'm gonna stay on if anyone has any questions, and we can keep talking. Sandra, question?
I have a question about the exam. I don't know, like it is already. Do you have the answer key?
Oh, yes. So I need to post, whoops, wrong class. I do have a key, so post the video key, and then we'll do a reflection as well.
When is the reflection due?
What do you think? Is Monday okay?
Is that okay?
I don't know.
Monday.
Tuesday?
Tuesday.
It doesn't matter to me.
Okay.
My focus really, I thought about not doing one, but I think it's a really good exercise for you to look through it. So my focus is for you to make sure you're learning the new content because we're so compressed time frame here. So I can put Tuesday. It doesn't matter to me.
So wait, you finished graded me, right?
Yes, you should see in the Dropbox. If you go in the Dropbox, you should see your feedback. I haven't uploaded grades yet.
Oh, okay.
Yeah, so, but if you go in the Dropbox, you should see feedback to your exam. Is that
And I have a
true?
question. Oh, sorry.
Is that true? Can anyone confirm? Because I did upload
I'm
them.
checking right now.
Okay, all right. So Talante, you were going to ask something?
You know how you record the sessions every single time?
Yeah.
Like, where are those located?
I haven't posted them yet.
Okay.
I had a couple students who had some delays. You know, normally it'd be like, you know, it's late. You got to take it before the next class period. But
Right.
but we're like,
Okay.
I'm
Yeah,
super
'cause I was
flexible,
thinking
super flexible now. So I have it up. It's just hidden. But I will post that as well. So I'll make another news post with the link to the video, and then reflection. We said we'll have that due by Tuesday. So that way you can focus on the quiz now, watching videos, and then if you don't get to it until Tuesday night, that's okay.
All right. Thank you.
Yep. Thanks for reminding me about that. I made the video. I have it all ready to go. I had it like last Friday, but I didn't want to post it because I had a couple students with some conflicts, and so that's why I was waiting to post it.
Okay. Thank you.
No problem. No problem. Okay. Yeah. So you can head out if you want. I'm gonna actually, maybe I can just stay recording. I don't know. I was gonna stop recording, just because it's kind of more personal. So
Yeah, so
I'm gonna
sorry.
stop the recording for now, and then you can hang out if you have additional questions. If you need to take off, it's 10:37, so that's officially the end of our class.